Sabko namaste. Today we will make a object detection model using transfer learning on our custom data sets. Before that, I will explain you object detection, what is object detection and what is transfer learning, so that you will not get confused during when we code. I will explain the code. Okay, so let's begin. So here is a brief definition of an object detection. Object detection means identifying object in images or video, finding the location, classify them. Basically, object detection model do three things: identifying the object in image, second, localizing the position of the object in image, third, classify that object. What type of object is that? For your understanding, I will give you one working of the object detection model. See, this is an input image. Then we use classify. What type of object is this? Then we'll localize that where the object is present, and finally, when we summarize this whole three things, we will get this type of image in which the classification is there and localization is there. Both things is there, and this is the working of the object detection model. These are some models with object detection models like RCNN, fast RCNN, faster RCNN, and YOLO. In our transfer learning, we use faster RCNN. Okay. In all models, whether it is faster RCNN, faster YOLO, detector, or SSD, all these model basically have one thing common. Not one thing, three thing common will be there. That input image, the backbone, and the head. Backbone basically can be a ResNet 50, VJ16, and there are many backbone convolution neural network. The working of this backbone is basically to extract the feature of an image, and this is the head, and this head is basically the final layer. The number of neurons in the final layer depend on the number of classes we have during a training time, but one neuron is fixed, that is for the background, and remaining neuron is depend on the number of classes which we have. Okay, now I will explain you what is transfer learning. Basically, transfer learning is in one word, in one sentence, I can say that using a pre-trained model. Now I will explain you why we use pre-trained model and what is its importance. Suppose we make a model from scratch and uh, we train that model on a huge data sets. If we train that, it will take some time. It takes week or sometime more time. So that's why we use a pre-trained model. A model which is trained on a large data sets like ImageNet dataset, Coco datasets, okay, which already contain 1.2 million images and 1,000 categories. Say 1,000 categories you can consider as a classes here. Okay, now I will explain you what is the importance of a transfer learning. First importance, I already told you, that is time. Uh, Training time is very crucial because we will not wait for the week for the training of the model. So that's why we use pre-trained models to minimize our training time. Okay. Second is useful weight. A pre-trained model already trained on a large data set, like ImageNet, which already contain 1.3 million images. So already that model already learned the complex patterns, very important patterns like texture, color, edge detector, already learned by their words, and their weights value is very useful, or we can say very powerful. So that's why we use pre-trained models, so that we can use that weights in our custom data sets. Now, domain. Let me read this definition, then I will explain you. Transfer learning is a concept where we utilize trained model in other domain, attain greater accuracy as well as faster training time. Suppose, let me give you an example. Suppose there is a model which is already trained on huge data set, which contain the classes like object, car, uh, truck, laptop, fan, etc., etc. These domain is something different from the medical imaging, where we use that model for the detection of the cancer or a brain tumor. But we can use that model, pre-trained model, which is trained on that type of classes like truck, pencil, boxes, etc. classes, because that model already learn the powerful patterns like texture, color, edge detector, which can also be used in this medical imaging also. That's why we can twist the domain also. Okay, or we can say change the domain. I explain you what is the importance of the transfer learning models. Now I will explain you what is the two types of transfer learning model, types of transfer learning. First is feature extractor and second is fine tuning. In feature extractor, basically we freeze the bottom layers of the convolutional network, and we replace the head according to our number of classes which we have. Okay, let me explain you. See this. Here we freeze this whole thing, whole convolutional network bottom layers, and we will replace this last neurons according to a number of classes which we have. This is a this last layer basically is a head, we can say, and this remaining is the bottom layers, and this is an input image. Okay, same. And in fine tuning we follow all the steps which we use in a feature extractor, like freezing the bottom layers and changing the head according to a number of classes which we have. But the twist is here that we not fully freeze the bottom layers. We partially we can say some layers we freeze and some layer we unfreezes. The layers which we freeze here is upper layers, and the later layers we do not freeze. We will remain them unfreeze for the training part. Why? Because the upper layer use learn the generic feature, but important feature is learned by the later layer only. That's why. Okay, so this is a two ways of method, we can say, for the transfer learning. We use fine tuning here for our transfer learning object detection model on our custom data sets. Okay, so let's begin creating the I will explain you each and every line of our object detection model using a torch on custom data sets. So let's begin it. So this is a folder, this is a dataset folder. Test images are 121, and in train we have labels which contain the annotation files, and images is these are the images which we use for the training purposes. Okay, let me open this in VS Code. I already opened it. Let me tell you the how the annotation file look like. See, this all values, I will explain you what this mean. This all are in a normalized form. This first value is the, we can say, the class label. This two values is the x centers and the y centers of an bounding box. These two values are the width and height of the bounding box. We have to first unnormalize them, and we have to use them. I will tell you how we can unnormalize them. Okay, let me code. So these are the libraries which we use for the training time. Let me run this. Torch vision, data loaders for loading the data, and transformer for the data augmentation, and for the change the image into a tensor format, because torch already always work on a tensor files only. Okay, see, removing annotation file with size 0. I already run this files, annotation files. In most of the files the size is 0, means it does not contain any bounding box values. Okay, so during training time it will give you an error. To protect the training time, or we can say to prevent the error during a training time, we have to use this thing. Okay, let me explain you. This is annotations label where the annotation file is there. Before removing the files, the size is 1521, and after that 1521. This first I will loop over the annotation directory, where I will go to the folder where the annotation file is there. After this, I will store the annotations file name in one variable, this in here. Treating over the annotations, I will make the path where of the annotation files. Okay, so here annotation directory and annotation file name. Okay, if the size, this OS path get size annotation file is 0, and it does not contain any bounding box values and labels, so we have to remove that file. Okay, so after that, removing the file, we get 121.521. It means there is no annotation file which does not which is empty, we can say. Okay. This is a class we have to use to load the data loaders, or we can say we to link the data loaders package so that our images and the labels are easily get loaded and we can use them for the training time. Okay. This is a constructor in which we passing the image directories where the trained images is there, annotations file directory, and the annotations. Annotation basically contain the list of all the annotation file name which we use for loading the images, and this transformer means converting the image into a tensor. Okay, these are the variables which where we store the variables value. This function basically return the annotations, length of the annotation. Get item basically return two output. First is two output. First is the image, and this is a target which contain the bounding box and the labels. Okay. First, the parameter is IDX, means index value in the annotations. Okay. By this this we fetch the annotation file name. Okay, and this IDX is with where you can say that the index value from the annotations list, annotation file name list. Okay, here we generate the image path. Okay, see this annotation file image directory, the where the image is present, and the annotation file name is we can say it is the name of the image of name of the image also. So that's why annotation file name can be act as an image name also, and be deleting last for, because we are deleting here dot in the last the file name contain extension also, so we have to delete this thing. That's why I'm using from 0 index till -4, means removing this 4 values and including dot jpg. Okay. After that we get the image path. We have to read that image. If the image is none, means something somewhere that image path is not matched with the image folder, so it will throw an error, and it will throw this type of error, file is not found. After that we have to convert this, because cv2 read image in bgr format, so we have to convert it into a rgb format using a cvt color function. After that we have to get the height and width. This why we are using the height and width, I will tell you, because we want to unnormalize the values. I already show you that the values in annotation is in a normalized form. Okay, here this annotation file is basically the path of the annotation file, how we get annotation directory and annotation file name direct. We can use this. This is the two boxes for the each image. Okay, we generate this boxes for each image. See, with open annotation file, it will open annotation file has a folder f, and we are iterating over the f, because suppose there is an image in which 2-3 beers is beers is present, so there will be 2-3 lines which contain the labels and annotation values, so that in one file this all values will be present. That's why we have to iterate over that. See, after using this function line dot strip dot split, we get the data in a index value, in a list in which each value is separated with the index value. Okay, and first we have to iterate the class name, as you already seen. Let me show you again. See, the first value is a class label, so we have to fetch the class index value here. Then the second value is a x center and a y center. This way first we fetch the value, and after that we have to divide this by the width. X center basically moving towards the right towards the right side, so that's why we have to act as a width of the image. So we have to divide it with the width to unnormalize it. Okay, same way for the white center, and same way for the width, because this value is in normalized form and we have to unnormalize it, so we have to convert it by multiplying it with the width and a height. After that, we have to achieve the x min and a y min. Let me show you one image to make it picture more clear. See, this is the height of the image, this is the width of the image, which we getting here. Okay, image shape, and see this x min and y min, this x center and y center, basically this x center and y center. Okay, let me close it. And this x max and y max is nothing. This x min and y min. Let me show you x min and y min. X min and y min is this, and x max and y max is here. Okay, this one. This value is x max and y max. This value is important for plotting the image. Okay, how I am getting this? So let me show you one more thing, that image coordinates not start from uh, bottom left corner. Let me show you one thing. See here, 0 0 value start from here. For the y, coordinates, 0 value start from here, and for the x coordinate, 0 value start from here. Okay, so we have to use these values to get the x min and y min according to that only. Okay, so how I will get x min and y min? So see, first I will show you how I will get x min. For getting the x min, we have to reach here. Okay, so for reaching this, we have to x min value, x center value, we have to plus the width divided by 2. If we divide this width divided by 2, we will get it. We have to subtract this values. Okay, see, from x center we subtract the box width by and divided by 2. Okay, x center minus width divided by 2, we will reach here. Now for reaching here, y value will be, see, y center minus box width, box height minus 2. See, I already told you that the image 0 0 value start from here, not from here. Okay, for getting this, we have to, from getting here, we have to minus the value height y divided by 2, because 0 0 value start from here. So to reaching it, we have to minus the value, minus the y center value by height by 2, height divided by 2. So this is thing. Okay, same way x min and y max. For x reaching the x min, first we have to reach here. So for that, we have to add a x center with width by 2. For reaching here, we have to add y center with the height y divided by 2. We will get y center by max value. This way I get the coordinates value. Okay, I will put it in a boxes dot append, which I have already created, and labels. See, here I'm not using that class index value. Let me show you why. See here, this fast center which we are using for our transfer learning, already trained on a COCO data set, which already said that 0 index is already fixed for the background, and the remaining is this. Total there is 91 classes including the background. Okay, and 0 index value is already fixed for the background. So to prevent the error during a training time, I'm not able to use class index for 0, because in all the annotations file, 0 is labeled as a beer, but we cannot use 0 as a label for the beer, because 0 index value is already fixed for the background. Instead of that, we can use 1, because we have only one uh, class, so that we can, so that's why we can use one insist of 0. So this way we will get the bounding box on labels. Okay, if f file contain multiple bounding box, it will store in the boxes. After that we have to change in a tensor format, because type PyTorch basically work on a tensor only. In self-flow transform means if there is any uh, annotations, or we can say changing in a file, in image, we can use that. After that we will store in a target variable and return that. Okay, so this way we create a class custom data set, which is used for by the data loader package for loading our data. Okay, now load pretend models to modify for the custom classify. Now this is a big point, this is the main point of the transfer learning. We have a number of classes, two background first and one custom classes for the beer. This is the line where we load the model faster RCNN. This is an object detection model, and for the backbone of the faster RCNN we are using ResNet 50 FPN. Okay, weights cocoa means we want a pre-trained model. Weight cocoa VN basically means we using a pre-trained model here. Now I already told you whether we are using feature extractor method or a fine tuning method. We have to change the head according to our number of classes which we have. Okay, let me run this. Okay, let me run this. I will explain you this tool line, why we are using this tool line replacing the classification head. So let me show you. I have printed a model. See, this is our whole model, convolution layers and a head, fully layers, all thing. See, this whole, this is our head of our convolutional neural network. See here, this box predictor past Russian. See, this is out feature is 91 years, means 91 classes. And here, see, what is out feature of 364 means, because if we multiply 91 into 4 means 4 coordinates, x mean, y mean, width and height, multiply by 4, it will give you 364, means the output layer contains these two values, 91 number of neurons for the classes including the background, and 364 for the bounding box. Okay, and see here this line, why we are using this line. In feature model.roi head, in model, go to the ROI head, go to the box predictor, go to the class score, and go to the inference feature. See, in model, go to the ROI head, go to the box predictor, go to the class score, and get the in feature. Why we fetching this in feature? Because when we change the head, we want to change the head now, because here the head is using 91 units, but we do not want 91 units because we do not have 91 classes. We have only two classes, one for the background and one for the beer. To get that what is the input of that last final layer, we have to use in features that how many numbers are connected to the final layer. So to know this, we have to use this line to get the features that how many number of input is connected to a final layer. So that's why we have to use this line. After using that line, we have to make मतलब means we have to replace that head which have 91 layers to our number of classes. Okay, we have number of classes here by passing the values in feature and number of classes here. Torch model detection faster RCNN, we are using faster RCNN, fast RCNN predictor as a classifier. Here we are using faster RCN as an object detection model using a ResNet 50 as a backbone. Okay, I will explain you in short. I will explain you. This is fetching the number of neurons which is connected to a final layer, replacing the final layer with our number of classes. We have two number classes, so we are replacing the order that. See, we are using fine tuning here because we want to train. We have to train the model according to our custom data sets. That's why we have to use this line. Dot for param model parameters, backbone parameters. In param there is a parameters. Basically here param is the parameter, and in parameter contain one attribute. One of the attribute is required grade, which tell the training time, which tell that it particular weight is wants to update or not. If we set true here, if we set true here means during training time we can update the weight. If I will use false here, it means during training time weight's value will not be changed, it will get freeze. What we want to change the parameter uh, during a training time, because we want to train the weights according to our custom data sets. That's why we are using this two lines. Okay, let me read already run it. See, after changing the head, let me show you. S- See, before changing the head, see, before changing the head, we have 91 neurons and 364 as an output of the bounding box. But now we have, when we change the neuron uh, last layer, or we can say head layer, we have out features two, because one for the background and one for the class, and eight number of bounding is for the bounding box. We have bounding box, we have four values, that is x mean, my mean, width and height. That's why we multiply by 2 into 4, we get 8. This is all, and this is here we generating the data loader, or we can say a data set. Train image data directory, train annotation directory. Here we are, train annotation basically contain the file name, annotation file name, all file names, creating the object of the custom dataset class which we have created, passing the variables according to parameters. First is the train image directory, train annotations which contain the file names, train annotation directory to load, which help in our to generating the images, and transform means converting the image into a tensor so that we can easily use that image in a training time. This data loader package basically use train dataset. I already told you that we have to create this custom dataset with three function, cat, item, and len, and this constructor, because data loader link that with the class and generate a custom dataset. There is batch size is 4, because means we have 1521 images which we divided by 4, which will get 381 batches, which include 4 images each. Shuffles is randomizations, and this function is important to load our dataset. Okay, let me run it. Let me run this one. See, we have 381 batches which include 4 images. See, here I am describing the optimizer and a scheduler. Okay, here we are basically sending the model to our device can be a GPU or a CPU. Here params, basically we are making a list of the parameters which can be updated in a training time. Okay, and this is here optimizer basically used to update the parameters. Here we are passing the parameter list which can be updated during a training time. Learning rate is 0.29. I want to say that during a fine tuning band, when we use the fine tuning method, the fine tuning method is because we do not drastically change the weights of the pretend model, because that model weights is important. I already told you that they already learned the important features, because you have to use that in a custom data set. So we do not change that value drastically. So that's why we have to use learning rates will be less. If the learning value is less, that's why just fine tune the weights. That's why this method is known as fine tuning. Okay, momentum is to give the direction of the optimizer. Here scheduler is basically used to decrease the learning rate values. Okay, at after third epoch. Step size is means after every third epoch it will reduce the learning rate value, and passing the optimizer for updating, and learning rate value will be multiplied by 0.01. Let me show you one example. Suppose we are using here 0.01 has a learning rate report for the epoch 1, and epoch 2 will be remain same because step size same. It means on third epoch it will change the learning rate value after third epoch, sorry, not in third epoch, after third epoch. Okay, so learning rate value in epoch 4 will uh, will be reduces and it will come to this value. Okay, okay, this is a problem in this. Let me make more clear. Okay, let me show you what is the meaning here. Let this after third epoch it changed the values. Now this act as a first, this act as a second, this act as a third. Now after third it will change the epoch value by multiplying the last learning rate value by 0.1 and reduce that learning rate. Reduce the learning rate value will reduce the chances of overfitting. Okay, that's why we use LR scheduler here. Let me run it. Now we have to check the data loaders. It is very important to check the data loaders that bounding box is correctly on a correct image, or box is on a correct position. So we have to plot the images with bounding boxes to check that our data set or data loader is correctly there. Okay, plot one row, two column. Figure size is 10 by 6. X level, converting the X in 2D to 1D. Okay, for better iteration over the subplots. This iteration data loader will first make a iterator over a trained data loader. With this function, next we will get the first batch images and the targets. Basically, target contain two. Target is a dictionary which contain two things: bounding box and the labels. Now we iterate over it since we just want to display two images, one row, two column. That's why we using two here, because go to zero it will go to 0 and 1 only, not 2 only. Okay, this animate image, because this show accept the format of the image is uh, HWC for visualization, height, width and channel. This image show accept this format HWC. But when we use this transformer to transfer, it's convert the image dimension to CHW. So to convert this dimension from this to this, we have to use permanent 1 to 0 and numpy to the, because this accept the numpy format also, and this format HWC, height, width and channel. Okay, now targets is equal to target.idx. Basically targets here, this images here is four images, and targets contain dictionary of boxes and labels of four images. So this target idx basically give fetch the bounding box and labels for the first image. This get the bounding box of the images and the labels. Now we have to iterate over it. So to iterate over it, we have to use this zip and box and labels, because there is more and more possibility that bounding box does not for in one image there is not possibility that only one beer will be there will more than one beer will be present, so though more than one bounding boxes will be there. So that's why we have to iterate over it. We have to first fetch this xmin by min, xmax by max values. After that, using that, we have to get the width and height of the image. Okay, by xmax minus x main will get the width, by max minus will get the height. Okay, this rectangle patches dot rectangle basically generate the bounding box. Okay, of color red and face color none, line width will be 2, but just passing we have to pass first coordinate x min and y min and just give width and height. It will generate the bounding box, and thus we have to add this patch in our plotting, or we can say subplots. We have to add text also to display the label, or we can say our classification, so that for that we have used this labels now. That's why we have to display this by using this label here. Okay, let me run it. It will take time, so please wait. So here is the image. See, our bounding box is correctly describing. It's going out of the bound, but because this lag is also going out of the plot. Okay, let me rerun it so that you can get that our bounding box and the data loaders which we have used data set is correctly describing. See, this is perfectly. See, this bounding box is perfect and this bounding box is perfect. It means the data set is correctly giving bounding boxes with correct image. Okay, so this is a training time, training part, training loss, so validation loss, list, iterating over the epoch. We have used number of epoch is 10. Let me show you. See, number of epoch is 10. Okay, starting a training time of epoch, model dot train. See, model, we have, this is important because now we are training the model, so we have to use this thing. Okay, now for each epoch, training of initially training running loss will be 0. This is displaying the masses. Now we have to iterate over a train data loader. This when we iterate over train data loader, it will keep two values, images and targets. Images contain 4 images and targets contain boundary box and label information for 4 images. Okay, and here we have to pass this to the device, same device, because our model in a if our model will be in a GPU and images and target in a CPU, then during training time it's all 101% it will throw an error. So to avoid the error, we have to make sure that model and the images and targets should be on a same device. That's why we have to use this value so that each image and images will be in a same device. And this target, see, first we iterate over a target for one image. Let see here, first we use this 14 a t for one image. After getting that, we have dictionary of bounding box and label. So here k is a key and v is a value. Let me if t dot iven first will be bounding box, key bounding box, v value values of the bounding box, and we putting that each value to the same device so that they will not throw an error. This way we are iterating over the targets and make sure that each value should be on a same device. Now here, now just passing these images and targets to a model for the training time. This loss static, what is the output of this model images and target will be this one. See, it will output 4 values: loss classifier, loss bounding box class regression, and loss objectation, and a loss RPN box regression. These 4 values will be passed. So let me read the definition. Lost classifier measure how well the model classify object into correct categories, means classification of the object will be first loss classification, and loss bounding box regression evaluate how accurate the predicted bounding box match the ground bounding box. These are this check how much the model is predicting correct bounding box values. And objectness means here we are using RPN and RPN. That's why this RPN basically tells that uh, the the anchor box which is created by the RPN uh, is on a correct object or name, means the anchor box include the image, include the object or not. The objectness means how much percentage is we can say that in particular anchor box or object is present. And same thing, if RPN using a bounding box, so there is a RPN box regression loss will be there also. That's why there is 4 losses in the will be passed by this model when we pass image and target. Loss classifier, loss box regression, and objectness, and a RPN box regression. We have to sum all these losses using this function. For loss and loss state values, losses, we will sum this. Okay. Now this is whole part is for the forward, passing the model, getting all the bounding boxes, values, and the classification. Okay. Now this is the backward pass. Why we are using this line object optimizer zero grade for each batch? Because if we do not use this, the values of the gradients here, zero grade means making the gradient values zero. If we do not use this, suppose when we iterate over the first batch, the gradient value will be 0.1. Let if the gradient values will not be set to 0, the next gradient value which is calculated will be like, suppose it calculated with 2, then total value will become 0.3, which is not good, because 0.1 is over, 0.2 is new gradient value. So to so that no value will be accumulated, or we can say use summarize that's accumulated. So we have to make sure that for each batch size zero grade will be used to change to make the gradient values to be 0. Okay. This is lost or backward. Basically, it calculate the gradient value with respect to the weight for each weight. Okay. After calculating, we have to change the weights. So for that, we use this method of this function optimizer.step. First, we make sure that gradient values should be 0 for each batch. Second, we have to calculate the weights values depending on the gradient and compute the gradient value. Third, since the calculation is done, we have to change the value on a change the or we can say update the weights. We have to use this function. After all this backward propagation, we have to that training running loss will lost or item, basically sum all the losses for each batch. After getting this, scheduler.step will be used, because scheduler.step is activated after the third epoch only, so there is no need to use that in a batch, or we can say train data loader time for loop. We have to use this scheduler.step in a for loop of the epoch only, because scheduler tab will activate it on a epochs, not on a batches iteration. Okay, now this train loss is used to load the train loss for the each epoch, and train running loss is used for that. Now this train data set, because here is training loss. This losses.ipom is for the batch for 4 images, not for the whole data set. Okay, that's why we are adding this. After getting the losses for the each images, we have to divide it by the train data set, so that we can get the average of its train losses. Let me run it. Okay, so let me come back when this iteration will be get over. Okay, so after completing the training, so the last for the epoch time, the training losses 0.0899. After that, we have to save the model. We have already saved the model this. Okay, now we have to test on our test images that how much our model is predicting the classification, how much our bounding box is correct on a correct position. So for that, same thing, we have to use this first import libraries, device, same thing, number of classes, getting the model, fast RCN R50, changing the last head layer, last head of the CN model according to our number of classes. Now we have to load the model which is already saved. This one. Okay, this one. This whole thing, this here to here, this is I already explained you each and every line uh, before in a code. Now at that time we have used model to train, because at that time we are training the model. but now we have to evaluate the model, that how our model is working, how much our model is doing good. Okay, now same model dot to, because device is important, GPU and CPU on the same device. Okay, this is plotting, this whole plotting is the same. I already in all the video I told you that the image, the pre-processing on an image done before the training had to be done same after the training for testing also, or when you use for the prediction, otherwise this will throw an error. So at the before training, we only use transformer to transfer to convert the image in a transfer format. This is a text directory. This is contain the file name of each in a text directory. Now we using this function, this OS path join to generate the path of an image, text directory, and random choice. We will select random file name or random image name from the random choice function from the test list files. Okay, this way we'll uh, load the image. We have to transform them because pre-processing important. And see and squeeze, here the size we can say, or here the dimension is uh, uh, let me show you. Here the dimension is channel, height, and width. Okay, after using a transform, but this model dot it image or tensor here, the requirement is, because on training time when we pass the model dot images, the size is a batch size images set. Let me show you. Here see images, here images dimension is not that CHW, not this much. Here's dimension is batch CH, and then W means batch, how many number of images in this images variable, channel, height, and width. Here batch size is 4, so means 4 images of CHW size. So same dimension we have to use, but we are using a single image. For single image dimension is this after using a transform, so we have to unsqueeze this, we have to add one dimension. After using the dimension, here's dimension will get, which we get is H1 C H, and W means 1 for the batch size, means one batch size which contain only one image of CHW size. Okay, same we have to use for two device. Means images should be on the same device where the model is. Now we have to use with torch no grade, which means no grading is required, no updatation or weights is required here during the evaluation time. And this image tensor 0. Here prediction, here prediction is in a list, and since prediction is in a list, and since the single image is there, so that's why for getting the prediction of the image of a single image we have to use 0 index value. Okay, that's why prediction will be get. Here prediction is basically give me the uh, list of the bounding box. See here, list of the bounding box, list of the labels, and list of the score. If the single image contain multiple beers, so that's why it will generate the list of the boxes, list of the labels, and list of the score. And see here, now we have to change the dimension for I am show, because I am show required this format, not this format. This format is required by PyTorch only. This format is required by the Matplotlib. Okay, so you have to use permanent 120 for change the dimension, and this variable basically store the boxes, labels, and scores. We have to zip that to iterate over them. Same thing will be there which I explained you before in a code. Okay, after this, let me run that. So here I already told you that the prediction will give me the list of the bounding boxes. This is labels, and this is score. Let me show you the score. See, scores. Okay. See, labels is here 1 means I already told you that 0 index is already fixed for the background and 1 for the class, but here we have only one class, that is beer, so that's one class 1 basically represent beer only. Okay. So this is this. See, our bounding boxes is correctly identifying the object in an image correctly. Okay, so it means our model is perfectly predicting the bounding box and class name. So our model is good. good to go on some other so for other object detection of that beer. Okay, so I have explained you each and every line of transfer learning for object detection on a custom data sets. Okay, so if you want this type of explanation more in and make your coding life more easy, please subscribe my channel, like my channel and comment below. Okay, my next video will be on transfer learning, same, but on a different custom data set. And now I will, for this time, for the next project, or we can say next code, I will use TensorFlow framework for the transfer learning. So to get the latest update, please subscribe my channel and comment and like. Okay, सबको नमस्ते.